Hello, welcome to part 3 of Chemistry Paper 1. So we've got to this question at the end of last time. It says the formula, okay, it's a little bit of a longer one, so we'll give a bit more time here to explain it to you all. So the formula of the iron oxide is Fe2O3. That's important, Fe2O3. Calculate the maximum mass of iron that can be obtained from 240 tons of iron oxide Fe2O3. Okay, so we've got 240 tons of iron oxide. Okay, so iron ore really. Okay, so we need to look at the formula mass, the total formula mass. That's why they've given us these masses of iron oxide. Fe2O3 equals, there's 2 Fe's, so you've got to be careful of that. 56 times 2, put that in a bracket. Plus an oxygen is 16, oxygen is 16, there's 3 oxygens. Okay, so that gives a total in our calculators of 160. Okay, so that's the formula mass. That gives you 1 mark. Okay, even just doing that will give you a mark out of 3 here. Okay, so the maximum mass of iron that we can get, okay, maximum iron, okay, is obviously 2. Okay, 2 lots of Fe, so 2 times 56, 112. So we're just talking about the formula masses at the moment. We haven't actually talked about how much we have. So it's just like a ratio. Okay, so let's how much we've got. So we've got 240 tons. That's right, the unit. Okay, 240 tons, but we have to divide that by our formula mass, so 160. Okay. And then what we can do, the next thing we can do is times 240. We can work that out. So 240 divided by 160. Let's do our calculators. Let's do my calculator. 240 times 240 divided by 160. 1.5. Okay, so we've got 1.5 times, let's look at our mass of our iron. Okay, so that's 1.5. Then we need to multiply that by the formula mass of our iron. Okay, and that will give us 168 tons. That's the end of the answer. But that's like a quick way of doing it. Okay, so yeah, we have to work out, it's like a ratio we had to do that. Keep my calculator out. Let's get the calculator out again there. I couldn't work that out in my head. So yeah, so it's a ratio, 1.5 to 112. So really we get rid of the oxygen there, aren't we? There are a few ways that you could do that. Okay, so if you experiment ways you can do this one. Okay, so it's not just one way of doing it, but that will score you 3 marks. Okay, nice and concise way of doing it. There are other ways you could do it. Even if you didn't get the whole thing right, there was lots of marks. We can get 2 marks just for trying to work it out. So always just try and get 1 or 2 marks just for trying to work that out, some ratios. Okay, so if you didn't get this bit, you get 2 out of 3 marks. Okay, so that's pretty good. So it's not as bad as that looks, that question, because even trying can give you some marks. Okay, let's move on to the next one. Aluminium cannot be extracted. So it's still part of question 3 here. It's quite a long one. So aluminium cannot be extracted by heating its oxide with carbon. Aluminium has to be extracted from its oxide by electrolysis. Okay, so they gave us some information. First of all, we need to use it. Aluminium is higher in the reaction series, okay, than carbon. So carbon, okay, so aluminium is too reactive. Okay, so I'll use the word reactive there. That's obviously the proper word. So aluminium, okay, is more reactive. Okay, so aluminium, that's a funny word to spell, is, but it's up there in case you've forgotten, is more reactive than carbon. Then carbon. So cannot be reduced by carbon. That would be the exact word we need to use there. produced by carbon. Okay. Predict the method that will have to be used to extract aluminium from its ore. If you can't displace it with carbon, you have to do it by electrolysis. 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 Just have to spell it. Okay. Let's have a look. Next one. In recent years, researchers have been investigating alternative methods of extracting metals from soils. Researchers have found that growing certain plants in appropriate areas can result in the phytoextraction of copper. Wow. Describe how growing plants can result in the phytoextraction of copper. Okay, that sounds difficult, but it's not as bad as that sounds. Phytoextraction just means the plants take it up, okay, they take it up from the soil. Okay, so the plants, okay, so plants absorb copper from the soil. So plants absorb copper from the soil. From the soil. Okay. And plants are harvested and burnt to leave the copper. So yeah, that's an interesting method, isn't it? That's why sometimes though is that some crops for eating aren't grown in certain areas because the plants will take up metals from the soil and make them poisonous. It's not the plant itself. Okay, so the plant's actually poisonous because copper and other metals are poisonous for us to eat and animals to eat. So you've got to be careful where you grow some things. Okay, in case they take up metals from the soil, but sometimes obviously it's done deliberately. But you have to know that you don't eat those plants, okay, that they wouldn't be edible. Okay, so 4A. So hydrogen burns in air at a temperature well above 100 degrees to form water. The boiling points of hydrogen and water are shown in figure 3. Okay, boiling point hydrogen minus 253. Okay, very low. Water 100. We know that one. Okay, use the information to add the missing state symbols to the equation for the reaction taking place as the hydrogen burns. Well, we're assuming it's in a normal condition. So hydrogen's a gas, so G for gas, plus oxygen goes to water. Remember, it said it burns well above 100 degrees. So the water, in this case, would be water vapor, steam. So also a gas. So it's a state we're asking there. So both G's, that's nice and easy. The atom economy for the reaction is 100%. State how the equation shows the atom economy is 100%. So all that means is that for the reaction, so all the atoms are involved. So all atoms in the reaction, so way of writing this is all, it's only one sentence, it says 1 mark, all atoms in the reactants, so in the things going in, okay, in the reactants are present, so they are there, are present in the product. So only one product is formed also, so only one product is formed. Let's have a look at the next one. Lead can be obtained by heating its oxide with carbon, okay? The balanced equation for the reaction is 2PbO. PB stands for plumbus, that's quite insane, plumbus, like plumbing, lead pipes. So 2PbO plus C, is carbon, goes to 2Pb, so lead plus carbon dioxide. Okay, calculate the atom economy for the production of lead in this reaction. So relative atomic masses and relative formula masses. So we don't actually have to even work those all out because they're done for us. Okay, so let's have a look then. Okay, we need to do the reactants first. Okay, so total mass Okay, so PBO, so we need to do 2 times 223. Let's put that in a bracket to show it's one thing. Plus, there's only one carbon, 12. Okay. Let's work that out. So our calculator is already here. So yeah, always have a calculator because you always need it for all science exams in biology. Okay, 2 times 223. Okay, equals 446 plus 12, 458. Okay, so that's total mass before, isn't it? That's a reactants. Let's write that down. So that's total mass of reactants. Okay. We've just worked out the formula mass of this bit. Okay. So we worked out the formula mass of that bit. So let's look at, so atom economy, we're looking at the useful, it's like efficiency. Okay, so mass of useful products, again, it's what we think is useful, isn't it here? So we want lead, don't we? Useful products. Okay, and careful here, because some people might just write 207 straight away, but it's 2. Okay, 2 times 207, that's one mistake, but it's okay. You still get some marks right in that. If you've made a mistake, you get what's called ECF, which is error carried forward. Okay, and times that by 2, I can do that one in my head, 414. Okay, so now it's like efficiency. So we do 414, okay, over 458. Okay, and then times 100 to get a percentage. Okay, because again, it's like efficiency, it's like a percentage, just to get a percent. You get 90. I already worked this out. Okay, 90.339, round up to 90. Okay, percent. Okay. Remember, it's just a useful product. Okay. Yeah, that's what I said. One of the things about the other question was that all the atoms are present in the product, and then one product is formed. That's what we do. We have to do a calculation on that. There's only one product formed. It's all useful. Okay, that's what we want. Part C. In an experiment to produce lead, 7.67 grams. Okay, again, look at the units. Very important here. Are obtained. The theoretical yield of lead for the experiment is 11.8 grams. Calculate the percentage yield of lead in this experiment. And so again, it's like efficiency, isn't it? Like, I think, well, we want 100%, but we don't get it. So we want 11.8, okay, theoretically, but we don't get it because it's real life and lots of other energy transfers take place. So this is again like, so 7.67 divided by what we think we'll get, and then we times it by 100. So it's just a bit of maths here again. Okay, so we would get 65%. Okay, just some maths for 2 marks. Nice and easy though. It's just remembering the percent sign about what we do there. When we see this, it's like efficiency in physics. Okay, it's also like saying what we want, what we get. Okay, when we work out, it's always in real life. That's happened obviously all the time. You never get 100%, and we're going to talk about here actually in question 4, see why we don't. In most reactions, pretty much all of them in real life, the percentage yield of any product is less than 100%. Give 2 reasons why the percentage yield is less than 100%. Okay, so one of them would be, so incomplete reaction. So reaction, pretty much most of the time, it doesn't all react. Okay, incomplete reactions. Okay, there's a few things we could write here. Another one would be unwanted side reactions. There could be other reactions going on. Okay, with the air, with anything, water, anything. Okay, unwanted side reactions. Okay, other ones, and then we've got our 2 marks here. Other ones could be loss of, it's usually like a practical one, like loss of the reactants, like the gas could escape out of the container. Okay, there could be the products not used up with the incomplete reactions. It could be obviously when if you're transferring it from container to container, you can get a loss of product. Lots and lots of things will give you marks. There's actually quite a nice answer there. So let's have a look at the next one. Number 5. Which of the following substances will be a solid at 20 degrees and will melt when placed in a beaker of hot water at 80 degrees? So melt will be a solid at 20 and will melt when placed in a beaker of hot water at 80. So it's going to melt, okay, 80 degrees. That's not going to melt 80 degrees. It melts 120, -7. And that one, they would most likely already be, it's a solid at 20. So they both are not solids at 20. So you might need to get a number line thing out to realize this. But if they melt, if that melts at -7, at 20 degrees, it'd be a liquid. If that melts at -32, at 20 degrees, it'd also be a liquid. That's the only one here that's a solid at 20 degrees and melts at 80. So the only answer there is C. If you want to obviously do some working at the side here, you can, like a number lines that's with melting, because that's quite confusing to think about if you're not used to it. Okay, a student set up the apparatus shown in figure 4 to obtain pure water from seawater. Okay, that's similar to what I was talking about earlier about sugar and water, but salt and water. Salt, so seawater, it's got salt in it. Okay, if you've ever been in the sea, you know about it, it tastes salty. Heat, pure water. Explain how the water in seawater separates to produce a pure water in the apparatus. So this is very nice and easy one. So the water boils, doesn't it? So the water boils. So we're heating it, water boils to form steam and leaves the salt behind in the beaker. So leaves salt behind. In the beaker. And steam condenses to form pure water. Nice and easy. Okay, so it says explain how the apparatus could be improved, okay, to increase the amount of pure water collected from the same volume of seawater. Okay, so what would happen is you could wrap the delivery cloth, wrap the delivery tube, okay, so wrap the delivery tube with cold water or ice you could use to make it condense faster and better as well, efficiently. Okay, and you just got to explain it. Okay, to increase the amount of condensation. Okay. A substance heated at a constant rate and its temperature is taken every minute. During the heating, the substance undergoes one change of state. And the result is shown in figure 5. Temperature is melting point. Okay. So A, B, C, and D melted. Explain the shape of the graph in terms of the changes in movement and the arrangement of the particles as the substance is heated. Okay, so let's go A to B. First of all, I think we'll go in order. So A to B, what's happening here? So A to B, so temperature rises, so graph rises as particles in the lattice vibrate more in a solid lattice. vibrate. Okay, B to C. So graph is flat. As melting is occurring, okay, and the energy is going in to change the state. Energy is put in to changing state. Okay, so it's melting, so it's going from solid to a liquid. Okay, so, and then from C to D, so graph rises again as particles move more rapidly, so faster, rapidly, and move past each other randomly. Okay, so I'm going to stop the video on that bit, and I'll see you in the next part for the next question. Thank you for listening. I'll see you in the next part.